When a fully loaded commercial haulage truck launches from a dead stop, the undercarriage absorbs a sudden, violent surge of kinetic energy. The tires must instantly convert massive rotational power into forward momentum through sheer friction. Making that momentum possible requires an engineering component tasked with two entirely conflicting physical mandates. The rear drive axle must simultaneously act as the vehicle's final torque distributor and its primary structural load-bearing member. This diagram illustrates the static and dynamic loads at play. The axle sits underneath the payload, supporting 40,000 pounds pushing straight down. Simultaneously, thousands of pound-feet of twisting engine torque pulse through that exact same space, trying to rip the internal components in a circular motion. Subjecting a solid piece of steel to both a massive bending weight and a violent twisting force simultaneously leads directly to catastrophic metal fatigue. Surviving this environment requires the complete mechanical isolation of the power transmission pathways from the structural weight-bearing pathways. This flowchart maps power flow in a standard heavy truck. Starting at the engine, power passes through the transmission and travels down the longitudinal propeller shaft. That drive shaft terminates at the rear axle, the final critical node of torque distribution before power meets the pavement. In standard rear-wheel drive commercial vehicles, the front axle is tasked strictly with steering and partial load-bearing. The rear axle bears the total responsibility for vehicle propulsion. To understand the engineering density of this final node, we will mentally build a heavy-duty axle from scratch, starting with raw incoming rotational energy and ending with a fully suspended structural system. Moving massive commercial tonnage dictates that engineers cannot simply scale up the size of standard components. They must manipulate the geometry of the kinetic energy right before it reaches the wheels. The mechanical buildup begins exactly at the interface where the longitudinal drive shaft meets the transverse axle housing. Sitting at the very end of the drive shaft is the pinion gear. It receives the raw, high-speed rotational energy coming straight from the transmission. This 3D vector model demonstrates the precise mesh between the pinion and the much larger ring gear. This forces the longitudinal power flow to take a sudden 90-degree lateral turn. Its secondary function is final torque multiplication. The massive size difference between the pinion and the large ring gear acts as a mechanical lever, drastically decreasing the output speed while proportionally increasing the turning force. This size relationship is defined as the axle ratio. A numerically high ratio means the ring gear is significantly larger than the pinion. High axle ratios generate the massive low-end torque required for haulage trucks and tippers to move heavy materials from a standstill. Conversely, specifying a low axle ratio shrinks the ring gear. This sacrifices peak pulling torque, but allows the wheels to spin faster, optimizing the truck for efficient highway cruising speeds. Multiplying torque relies on straightforward gear ratios, but possessing immense turning force is useless if it cannot be smoothly delivered to two wheels fighting entirely different physical paths. Using a single solid axle shaft presents an immediate geometric flaw. During any turn, the outside wheel is forced to travel a physically longer arc than the inside wheel. If both wheels are locked to the identical rotational speed of the ring gear, the tires will violently scrub against the pavement, causing severe driveline binding and eventual mechanical failure. This wireframe view isolates the internal mechanical solution housed inside the rotating ring gear, the differential gear set. When the truck enters a curve, resistance slows the inner side gear down. This forces the small spider gears to rotate on their pins, driving the outer side gear faster, dynamically splitting torque while permitting different wheel speeds. The critical weakness of this open differential design is that it sends power down the path of least resistance. If one wheel hits ice or deep mud, all the available torque spins the slipping wheel, stranding the vehicle. To mitigate this in light off-road conditions, limited slip differentials utilize internal friction modifiers and clutch packs to maintain resistance, successfully preventing complete spinouts. For military and heavy construction applications, locking differentials use mechanical pins to rigidly bind the side gears together. This overrides the differential action entirely, ensuring equal power reaches both wheels in extreme environments, regardless of slip. The differential solves the complex kinematics of steering. However, it leaves the massive physical weight of the truck payload pressing directly down on these delicate rotating shafts. The axle shafts must now carry this multiplied, balanced torque outward to the wheels, while the truck's 40,000-pound payload continues to push straight down. This cross-section details the semi-floating axle design common in light passenger trucks, where the wheel hub bolts directly to the end of the axle shaft. In commercial haulage, this exact architecture fails. The spinning shaft is forced to act as a weight-bearing beam, subjecting the steel to relentless, cyclical bending moments on top of severe torsional stress. The heavy-duty solution is the full floating axle architecture, which entirely redesigns the wheel hub interface. The wheel hub no longer touches the axle shaft. Instead, it rides on massive bearings mounted directly on the outside of the static axle housing tube. This establishes a new load path. The vertical payload weight flows through the rigid outer housing and directly into the wheel hubs, completely bypassing the internal shaft. The axle shaft itself now freely floats inside the hollow housing. It bolts onto the outside of the wheel hub via a heavy flange for one purpose only: to deliver rotational power. Freed from the burden of the vehicle's mass, the shaft deals exclusively with pure torsional twisting force, drastically extending its fatigue life. To achieve this isolation, the external axle housing must be massively reinforced. Manufacturers utilize thick cast iron or heavy fabricated steel, specifically designed to absorb extreme radial loads without deflecting. The full floating architecture demonstrates that commercial-scale durability is achieved through the geometric redirection of forces, rather than relying solely on material hardness. Even a massive full-floating axle has its limits. Extreme haulage payloads will eventually exceed the maximum load rating of the hub bearings and the tires themselves. This technical rendering displays a 6x4 tandem axle configuration, which adds a second linked rear drive axle to expand the vehicle's payload footprint over a wider surface area. This immediately introduces a new driveline complication. An inter-axle differential must be added to the forward drive axle, tasked with splitting the incoming propeller shaft torque evenly between the front-rear and rear-rear axles. To manage the physical weight distribution, load transfer mechanisms like equalizer bars or walking beam suspensions are installed, keeping the weight balanced across all four wheel hubs, even when climbing over jagged, completely uneven off-road terrain. Multiplying the axle count to carry additional tonnage requires building an entirely secondary network of kinematic and load balancing systems just to maintain the vehicle's structural equilibrium. Even with perfect structural isolation, the microscopic reality of metal meshing under extreme torque generates immense friction and destructive heat. In highly loaded environments, specific failure modes arise. Fatigue cracks propagate through twisted shafts, bearings suffer spalling from micro-misalignments, and gear teeth score from overheated, thinning lubrication. Engineers combat this degradation at the molecular level. Specialized forging processes are used to perfectly align the grain structure of the steel axle shafts, maximizing their resistance to twisting forces. Heat treatment processes, specifically induction hardening, are applied to the gears. This creates an incredibly hard exterior case to resist continuous wear, while leaving the internal core of the steel ductile enough to absorb sudden shock loads without shattering. Brilliant geometric design only survives the realities of continuous commercial hauling when executed with exacting material science and targeted metallurgy. Today, commercial drivelines are undergoing a massive transition as electric vehicle architectures begin replacing heavy internal combustion layouts. This side-by-side comparison contrasts a traditional layout with the modern E-axle. In an EV configuration, the massive longitudinal propeller shaft is completely eliminated. The E-axle integrates an electric traction motor and planetary gear set directly into the space where the traditional differential sat. While the power delivery system has shifted from combustion to electricity, the underlying physics of managing a 40,000-pound payload remains constant. As power systems evolve, torque multiplication, kinematic differential action, and full floating load isolation remain the functional requirements for heavy vehicle performance.